Hello and welcome to a series on excavation support system design. Today is the first of a series of videos that you'll see where we're going to be going all the way through the basics of soil pressure, all the way through the design of a sheet pile wall. Our learning objectives for today, though, are to explain the difference between the at-rest condition, active pressure, and passive soil pressure. And what I'm showing you on the screen right here is really to put this whole problem into context so we can understand what we're going to be trying to solve. Let's take a scenario here where we have a 10.5-foot excavation. We're going to excavate the soil on this side of a soil retaining wall, a cantilevered wall. We have a retained soil in the back here with some soil properties, including a unit weight and a friction angle, which are things that hopefully you've heard of before. We'll talk about what Ka and Kp are shortly. One of the assumptions, or we have a couple of assumptions that we have to state before we move forward. The first is that we have a consistent soil profile in the entire problem. That means that everything that we see here in this problem, all of these regions have the same soil with 120 pounds per cubic foot unit weight and a friction angle of 30 degrees. Another assumption that we're going to make is that we have a cohesionless soil that we're supporting. So sheet pile walls, this is what this is representing here, a sheet pile wall, they're really aimed at supporting the load, the lateral load of the soil in a retained side when we've excavated on the other side. What we're going to do in this series is we're going to go back and forth between this problem here, and a tutorial that we have in PowerPoint. So let's open up this tutorial quickly and start to talk about the situation that we have. Let's take a unit of soil that is somewhere below the surface of the ground where we would be hanging out. At this point, anywhere underneath the ground, as long as we have no excavation and no strange forces going on, everything's at equilibrium. And we know that it's in equilibrium because there's no motion, there's no rotation. So we know the sum of our forces and the sum of the moments and the sum of the stresses are all equal to 0. But when we excavate on one side along a plane, say along this Y plane, what we do is we're removing one of those internal stresses. And the result is an imbalance of forces. And what this unit of soil now wants to do is translate to the left, because we have a pressure here, sigma x, moving to the left that's unsupported. Now our excavation support system is going to support that lateral earth pressure so that we don't have the soil collapsing into our excavation. It's a very important safety issue. So this is our lateral earth pressure, sigma x. What we also know, though, is that we're going to be excavating along a plane. Let's say we're going to have a long wall along the Y direction. What we know is that along that Y direction, everything is going to be at equilibrium because that's our plane that we're excavating against. We're also going to have equilibrium in terms of the Z direction, but we're going to need to know what that Z force is in order to translate to our X force. And we'll talk about that in just a little bit. So we can actually take that sigma Y away because it's going to be consistent along the profile of our wall. Now we end up with this problem where we need to know the lateral earth pressure, but that's a very difficult thing to measure in the field. What we can measure is the vertical pressure, our sigma z. We know that we can measure sigma z because sigma z depends on the weight of the soil above that point. Now K is a great coefficient that allows us to translate from a vertical pressure to a lateral pressure or a horizontal pressure. And so K is really the ratio between sigma x, the lateral earth pressure, and sigma z, the vertical earth pressure, which exists because of the soil or any surcharge load or any load that we have above that point. Excuse this. So what we need to do is we need to understand K a little bit more. And I'm just going to skip over this slide here, and we'll talk a little bit about K. Let's go to our worksheet here really quickly. Open up a new tab and talk about this for just one moment, because I think it's important to understand the passive and active earth pressures and just lateral earth pressure in general. Let's say we have a solid. And I'll draw this out as a solid block. If we have a solid and we apply a force, say with our hand here, we'll call that sigma z. If we apply a force there, the question is, what component, if this is a solid block of rock, how much of that force is going to translate into sigma x? Meaning, how much of our vertical pressure from our hand pressing on this rock is going to transfer into the lateral direction? Well, the answer is almost none, or practically none. And so if we were to graph this out, what it would look like is, if I was to graph out sigma z by sigma x, as sigma z increases, as we press with our hand more and more and more, the actual lateral earth pressure, sigma x, still remains about 0 or very, very small. Now, if we think about this in terms of a solid, so this is our solid, what we know is that we can press pretty much as we want until we reach failure before we're going to have any translation into a vertical direction. Let's instead take a look at something like a cylinder full of water. Okay, so this is a cylinder full of water, and now my question is, what forces are on this? Well, we actually have a sigma z in this direction, where really this is just the atmospheric pressure. If I was just to leave this cylinder open. Now my question is, if I was to open this, a gate in this, what's going to happen? Well, of course, we're going to have that water run out. And so what's going to happen, what we end up having here is, if we graph this out, is sigma x by sigma z again, and where sigma z is just the atmospheric pressure, really all of that atmospheric pressure is translating into a horizontal component. So it's a 1-to-1 ratio. Okay? For water, this is for liquids. And the reason that liquids behave that way is that liquids are allowed to flow freely. Right? They're actually vibrating particles, and they can flow freely against one another. And what we end up having is a direct 1-to-1 relationship between the pressure of the atmospheric pressure and the pressure above a given point. So this right here would be the pressure of the water above that point plus atmospheric pressure, and that's going to translate directly into a horizontal component. And we know this from our water classes. So our profile is going to look a little something like this, where we have atmospheric pressure up here, and we are going to increase in a linear fashion as we go deeper down, and that's going to be our lateral water pressure. Now, soils are somewhere in between. So we know that the range of where soils are going to behave is going to be somewhere in this region, where this is sigma x and this is sigma z. Now, what we need to understand, though, is what those values are. So if we remember, K is equal to our sigma x over sigma z, we know that that value is going to be somewhere between 0 and 1. Okay? So let's go back to our PowerPoint here and talk through the different earth pressure conditions that we might have. Let's make sure we don't get this again. All right. So let's maximize the screen. Now we know we need to resist that load, but some of the systems, we really have 3 conditions that exist in the soil. And they're going to define what our lateral earth pressure is. Let's say we have a reinforced concrete wall. That's what's being represented by this large gray block. If we have a reinforced concrete wall, the way that we typically will construct that wall is by using a bentonite slurry, and we leave the stresses in the soil in place. Okay, this is what we call the at-rest condition. We don't introduce additional stresses. We don't take any stresses away. Okay, so this soil wall, this reinforced wall, must then support our sigma x, which is the lateral earth pressure. If we don't allow the wall to move or flex, if it's unyielding and it does not move, and it's rigid and unyielding, what we do is we have that soil pressure contained. And I like to use this kind of analogy to this as a bottle of soda that's under pressure, that where we haven't twisted the cap yet, but we haven't also added additional squeezing to that bottle. It's just at its condition that exists, naturally. Soda's not natural, but you get the idea, where we have that lateral pressure. Okay, we insert the wall, and that lateral pressure stays. This is what we call the at-rest condition. Okay, now what we know from lab tests is that we have this at-rest condition, which we're going to call K naught, where we have the relationship is 1 minus sine of phi, which is your friction angle, times the over-consolidation ratio raised to the power of sine phi. What this is telling us is this value, our at-rest earth pressure, depends on the natural failure plane, our friction angle, the angle of repose, and the over-consolidation ratio, which is the ratio between the pressures that exist in the natural state and any induced pressures, or the maximum pressure that it can withstand. Okay, so that's our over-consolidation ratio. Over-consolidation ratio is actual stresses over maximum stresses. We're going to use 2 in this. That's typical for these problems. Okay. Now, when we're trying to figure out what our lateral earth pressure is, we know K is going to help us translate from a vertical soil pressure to a horizontal, and we can easily measure vertical soil pressure. Okay. Now, our vertical soil pressure is the weight above a given point. All right. Let's say H is the depth that we're going here. H is the depth of the soil, and gamma is the unit weight or the density of the soil. Now, the pounds per square feet at any depth here in the vertical direction is going to be simply the density of that soil multiplied against its height. Okay. Now, what we can now do though is we know that vertical pressures increase with depth, and the horizontal pressures also increase with depth. We can relate them through K. So if sigma z is gamma h, and we know that K is sigma x over sigma z, we can simply solve for sigma x by finding gamma h times K. That's the weight of the soil above point H, at depth H, multiplied by our, in this case, the at-rest earth pressure. That's going to give us our lateral pressure. It's really nice because the lateral earth pressure is something that would be quite difficult to measure in the field. Okay, so if that's H, we're going to actually solve one of these problems here in the next module, but we're going to move forward. And so this is the at-rest condition. Now, this condition is going to be kind of moderate. We're going to see 2 other conditions that are on either side. One a little bit less than the at-rest condition, and one quite a bit more than the at-rest condition. Okay, so this is just relating mathematically what we've already talked about, where we put our equation for K naught into our equation for our lateral earth pressure. Now, when we have a sheet pile wall, what we allow that sheet pile wall to do, and now this is not a reinforced concrete wall, not something that's going to be rigid and unyielding, but a sheet pile wall, we will allow that wall to move very slightly. At the top of the excavation, we're talking about just a fraction of an inch or just a little over an inch. And if we allow that excavation support system to move very slightly, it's very similar to an analogy where we open up the cap of that soda bottle just a little bit. By just opening it up a little tiny bit, we allow a lot of that pressure to dissipate. If we allow our sheet pile wall, for example, to move very slightly, or any cantilever wall for that case, we end up with what we call the active case, which is a soil pressure that is much less than the at-rest condition where all of the stresses remain in the soil undisturbed. Okay? Now, the amount of movement you need to reach the active case depends on the different kinds of soil that you have. Now, like I mentioned before, we're going to assume cohesionless. So we're talking about 0.001 times the height of your excavation, which is going to be a matter of a fraction of an inch. What this is saying is if you allow that wall to move just a fraction of an inch, you are going to dissipate a lot of the pressures in that soil by allowing the soil to relax. Okay? Now, by allowing that soil to relax, we end up with what we call the active case. And this guy Rankin did some great laboratory tests and field tests and found that the active earth pressure is equal to the tangent squared times 45 plus the friction angle over 2. Okay? Now, we can get into you should get into this into your soils classes about why this is what it is. We're not going to derive it in this series for you. We're just going to assume a Ka value. Okay? Now, I use this as another analog here, is that it's kind of like pushing an object down a hill. Still might require some force, but a lot less than if you were to push it on level ground. But if we look at the bottom of this excavation, we can see that the tip of that pile, if we allow that to rotate at the top and allow the soil on the retained side to relax, if we allow that soil to relax, and this pile to rotate, what happens is we actually move against the soil down at the bottom. So if we look here down at the bottom, the tip of this pile is going to be moving into the soil. The top here is going to be moving away from the soil, and this pressure up here is what we call active soil pressure. Now down here on the retained side, that tip of that pile is moving against the soil, and that's what we call the passive case. Because in order for that to move freely against that soil, it's got to overcome the passive pressure, and the passive pressure is very high. That means we actually have to overcome the shear stresses of all the soil above this point in order to get that required motion down here. Okay? So with the passive case, we still have to consider the weight of the soil above, and we're going to have a different K, a different coefficient that translates our vertical pressure into a passive pressure. Okay? In order to reach the passive pressure, we need a little bit less motion. Okay? We don't need to move quite as much against the soil to reach the passive case. You can see here with our dense cohesionless soil, it's 0.02 times our height. A lot more motion than with our active case, but in any regard, it's still a very small amount of motion relative to the height of the pile. Okay? According to Rankin, the passive pressure is actually very similar in the way that we compute it to the passive, or to the active, where we're just taking the squared tangent of 45 minus phi over 2, which is my analogy again here is like pushing an object up a hill, or taking that bottle of soda that's under pressure before we twist the cap and squeezing on that a little bit more. The internal pressure there is going to be very high. Okay? The next lesson we're going to go into is force analysis, so I'm going to leave you here with this. I hope you enjoyed this and hope you learned something from it.